Welcome back, students. In the previous classes, we have looked at some key concepts in thermodynamics. And to explore this subject further, we need to have some definitions, uh, or we need to be at this common page or at the same page on with regards to some definitions that we popularly or commonly use in thermodynamics. So let's look at some important concepts and terminologies in thermodynamics. First of all, we need to talk about a few key concepts. What is a system? What is a boundary? And what are surroundings? So a system is defined as a region in space. A system is defined as a region in space which we are considering for analysis. For example, in a car, you have an engine. You have an engine. So if you are analyzing this engine, the engine turns into the system. In motors or in any power plants, you have got a generation unit, a thermal unit, and then after the generator unit. If you're analyzing just the generator unit, that the generator turns into a system. The system boundaries, the the edges of the systems can be defined as something called as boundaries. All right. Now these boundaries can either be fixed or they can be moving. They can also, in some cases, they can allow the flow of matter and energy across them. Everything outside the boundaries, everything outside the boundary of the system is termed as the surroundings. And the system combined with the surroundings is termed as the universe. All right. So we have talked about three important definitions. What is a system? What is a boundary of the system? And what are the surroundings of the system? And the combination of system and surroundings, which is the universe. All right. Then we need to talk about something called approaches. In the previous class, we talked about temperature. While talking about temperature, I spoke about how we actually conceive the concept of temperature, or how we understand the concept of temperature. How we defined the temperature was that we looked at temperature as the average kinetic energy of the individual molecules. All right. So while examining temperature, we actually were looking at individual molecules, or we're looking at the entire setup at a molecular level. Okay. So in this way, in this case, we were analyzing the system in a microscopic approach. While measuring temperature, we were trying to measure the average or the kinetic energies of each of these molecules, the position, right? So this was an example of something called microscopic approach. Obviously, that fell apart quite quickly when you're talking about multiple, many atoms. For example, the number of atoms that make the pen which you're holding, or the table or chair which you're using right now. So in this case, what we need to do is we need to group these molecules into lumps of matter. So when we do that, we follow something called as the macroscopic approach. So you have got the microscopic approach when you are looking at individual molecules or a few molecules, and then figuring out their velocities, their positions, and things of that sort. Okay, and then you have the macroscopic approach. Now the microscopic approach is also known as the statistical approach in thermodynamics, and in most cases it's not really widely used for obvious reasons, that you cannot uh, accurately measure each molecule's kinetic energy or its position or its velocity or whatever attribute that you want to assign to it. All right. Next, we need to talk about, as we have already talked about systems and surroundings, we are going to try to classify these systems. The way we classify systems is as open system, closed system, and an isolated system. Now, as I said, a system is a region in space which is being analyzed. Okay, the system has edges or is limited by in its whatever limits that you're defining are known as your boundary. Everything outside the system is known as a surrounding, and the system plus surrounding is known as the universe. So now these, as I already mentioned, you can have mass and energy both flow in some cases, or you can have only energy flow across the boundary in some cases, or you can have neither mass nor energy flow across the boundary in some cases. So on the basis of this, we define something called open, closed, and isolated systems. So an open system is known as a system where mass as well as energy can flow across the boundary. For example, you have a tap. You have a tap. So in a tap, what is happening is that if you are analyzing this system, you can see that water is flowing in, water is flowing out, correct? And as soon as the water flows out, what happens is that it's dropping in height. So your tap is at this height, it eventually comes down to this height. So obviously there is a change in energy level, right? Your potential energy changes to kinetic energy, isn't it? So there's mass as well as energy flowing across the system, correct? Then in a closed system, for example, you take a box or a bottle. In a closed bottle, or say in a pressure cooker. In a pressure cooker, what you're doing is that at least till before the whistle goes off, you're heating this entire system up. You're heating the system up, and that causes the pressure to rise. And till before the whistle goes off, the contents of the contents of the cooker cannot escape. So that's mass cannot cross the boundary. All right, but since you're adding heat to the or adding thermal energy to the entire system, you are adding energy to the system. So energy is crossing the boundary. So this is an example of a closed system. Then comes something called an isolated system. Here neither energy nor mass can cross the boundary. The most common example that we can talk about is thermos, a thermoflask. All right, I'm assuming each one of you all have experienced this or at least seen this in real life, wherein you keep your contents either hot or very cold. On a cold winter morning, probably you want a nice hot cup of tea, so you make tea early in the day, and then after you have it throughout the day, right? So you're keeping that entire contents within the thermoflask, so there's no mass flow, and at the same time the thermoflask keeps the heat within it, so there's no energy flow across the boundary. All right, we also have to talk about a subset of isolated systems called adiabatic systems. All right, so as I've just mentioned, these are a subset of isolated systems. Now an isolated system is a system in which there is no heat, no energy transfer, and no mass transfer. This is an isolated system. No mass transfer across the boundary. In adiabatic systems, there is no heat transfer across the boundary. All right. So in this case, there is no heat transfer. In this case, there is no energy transfer. You have to understand this is a very, very important distinction. For example, in the case of isolated systems, I talked about a thermoflask. All right. In a thermoflask, say this is a thermoflask, and here you have got some liquid kept at temperature, say a very high temperature T. Say the temperature is 1000 degrees Celsius. Okay, and you want to maintain this at 1000 degrees Celsius. So what you can do, what we would have done normally is that you put this in a nice and isolated insulated system and ensure that there is no heat transfer across the boundary. Now say if you wanted to increase its temperature, what can you do? So what you can do is you can introduce an heating element here. You can introduce a heating element here, and what is happening is that as the heating element, there's electricity passing through the heating element, this temperature starts rising. Okay. Now in this case, what is passing through the boundaries of the system is not heat, it is electrical energy. Okay, so there is no heat flow across the boundary, but there is electrical energy flowing across the boundary. So this is an example of an adiabatic system where the walls are insulated, but there's electricity flowing across the boundary. Okay, so these are adiabatic systems. Now, adiabatic systems have something called adiabatic walls. Adiabatic walls. Adiabatic walls, by their definition, do not allow heat transfer across them. The opposite of adiabatic walls are known as diathermal walls or boundaries. These allow energy or heat transfer across them. So you have got adiabatic walls and then you have got diathermal walls. Adiabatic walls are in adiabatic systems. Diathermal walls basically allow heat transfer, so they can be in open systems or in closed systems, whichever you're considering. Okay. So speaking of open systems, we need to talk about something called as control volume. So for example, in an open system, where you have got mass entering the system and mass exiting the system, and we want to analyze just this small region in that entire setup. We've got something, say there's a pipe, there's water entering the pipe and there's water exiting the pipe, and we want to just analyze what is happening in the middle of the pipe. Okay, so this region which we are analyzing is going to be termed as control volume. Okay, so and control volume is a region in space of importance within an open system. So within an open system, this is an open system, mass is flowing in, mass is flowing out. We are analyzing a tiny bit of that area. Okay, so this is something called as a control volume, and its boundary obviously is termed as control surface. All right. Okay, so far what we have talked about is the macroscopic and microscopic approach. We have talked about the definition of system and surrounding, and along with the boundary, then we have also talked about something called the universe, whereas the system plus surroundings is equal to the universe. Okay, then we have defined different types of systems such as the open system, closed system, and the isolated system. Then within the open system, we have talked about something called as the control volume and the control surface. All right.